In this demonstration, we're going to do a double replacement reaction, and this is where basically both pairs of ions will actually split in each individual compound and then basically change partners. So the potassium is currently with the iodide in this one, the iodine ion, and then the lead is currently with the nitrate in this ion, in this material and compound. And what happens is if we dissolve them in water, that water allows them to break apart into their individual freely mobile ions. So we're going to take a little bit of each. We're going to take a little bit of the potassium iodide. Now in both of these containers of water here, I have distilled water, so there's not a reaction with all the other junk that would typically be in your water. And so we're going to try to do an equal amount in each. So I'm going to leave that one in here so we know we're using the same stirring device and not having cross-contamination. So there's our potassium iodide. And then in the lead nitrate, I'm going to do another similar amount. Not going to be exact amount. This is more of a qualitative experiment. And so here we go with this one, about the same amount. And so this is going to be more qualitative, not quantitative, because we want to see the instant results of what happens when you have something like this and you put them out there into the real world. Okay, so we're just going to continue stirring these up a little bit. Some might have a little better solubility than the others, and so we can see down at this one, I also could have added a little bit more. I tried to have the same amount of water in each, but again, if you are taking chemistry in New York State and you're familiar with Table G, the solubility curve table, that every single material has a different solubility at similar temperatures. But for the most part, we got them together. And I do want you to make an observation that, relatively speaking, both liquids are clear. The one on the right has just slight cloudiness to it, just because there could be some other residue in there. But basically, we have, pretty clean beakers, and again, a similar amount in each case. And so what happens though, if we actually remove these, I'm going to just take these out for the time being, dry them off quickly off the camera. And if we just take our samples, they both look clear. And I'm going to take a pipette, or I have a pipette, I'm going to disperse one into the other. And what happens is the double replacement reaction is going to take place. And so what happens is I have, for example, in this container, I have potassium and iodide. So I have K and I have I. And then over here I have lead, Pb. And then I have the nitrate, the NO3. And so what happens is now the K, which is a positive ion from this one, can react with the NO3, which is a negative ion here. And vice versa, the positive ion of lead on this one can react with the negative iodide ion here. And so we will see what we get here. And so I'm going to take a sample of the lead nitrate, and we're just going to go over here, and instantly, as soon as we start to drop it in, you should start to see some amazing little colors and reactions take place. And that's because instantly I now have these available ions that are now going to have the ability to react. And so the lead that's readily available in the pipette is reacting with the iodine, which is readily available in this left beaker. And so what we get as a byproduct is lead iodide. And what lead iodide is a precipitate. Okay, it is a solid material. It's not soluble in water, so instantly these things form and they start shooting in different directions. Okay, and so it's a really, really, really cool experiment in double replacement. And so I want to do this again on a different scale, and just to show you the idea, you could see when it went in there that the water is always moving. You could see it going in different directions. And so we're going to move these kind of off screen. We're going to try another little experiment, and if we look close, it's kind of hard to see right now just because I'm at an angle, but what'll happen is you can start to see a thin layer at the top because this is a heavier material. This is going to settle out, and that's what precipitates do. If you think of the word precipitation, kind of like rain, sleet, snow, hail, anything that's going to come out of the sky and settle down, this will settle down. So if I just leave this over the course of the day, it will all be down to the bottom. It looks a little thicker that way, and you can see some of the solids start to come together. If I had a centrifuge, if I wanted to whip it around in a circle, I could actually get it to settle out a lot faster. And so we're going to try another little experiment here. And I have a third test tube, or third beaker, which is just distilled water. And so I got regular water and I got the other two waters. And so I'm going to grab one more container, because otherwise I won't be able to make the experiment work. So bear with me for 1 second here as I go into the lab table. I'm just going to mix up a little more of the potassium iodide because, again, we already have that sample ready and it changed color, so I need a fresh supply. So I just quickly mixed up a new one. So we have, over here on the left, we have potassium iodide. In the middle, we have just distilled water. And on the far right, we have the lead nitrate. So I'm just going to grab this, dry it off quick, set it down. Then we have our 3 pipettes because, again, we don't want to have any cross-contamination. So we'll see how this works and see how well it comes out. So keep your fingers crossed. Going to carefully put a little of the lead nitrate on one side and a little of the potassium iodide on another. And of course, when this happens, of course, we don't see anything happen. And I want to try to give equal amounts. And I'm hoping they don't touch yet. And so if we just let them sit there, this is a curved little container and a curved little area. So I'm going to give a little intermediate with some distilled water in between and let those two do some work. And so notice, as soon as they start to contact, we can see that that water is continuing to move and to evolve into this new compound. And so that motion of the water being a liquid, it's always in a state of constant motion. It's always moving. Even though it might not look like it's moving, it is always moving. So as these molecules are moving from the right side onto the left side and the left side on the right side, they're both making contact because, again, the lead is freely able to move through and the iodine is freely able to move through. And that's what you have to have. You have to have mobile ions in order for these to actually take place and to have contact. And then at the end, of course, if we were to really kind of swirl it around a little bit, maybe give it a little bit of extra, energy in there. I'm just applying my own little energy. And notice now it looks pretty consistent all the way through. And if we take a closer look, not sure how well this will zoom in, you can actually see some of the pieces that look like solids and little chunks that would settle out over time. If you were to put this into a centrifuge or just spin it around, or just even over time, just leaving it out overnight, this would settle out, and all of the other materials, which would be known as the spectator ions, that would be the potassium and the nitrate. And so they would be the clearish looking liquid that is surrounding that. Again, those are called spectator ions because they're not part of the actual like solid product at the end, but they are still part of the overall solution. So again, this has been a double replacement reaction with potassium iodide and lead nitrate to make the precipitate lead iodide. This has been Mr. Gardner, and hopefully you've enjoyed and pulled something out of this chemistry demonstration that will help you in your classes.